Assalamualaikum. Welcome back to Sir K Labs Physics and Chemistry tutorial for high school students. In this episode, we tackle three problems involving image formation by concave and convex spherical mirrors. So stick around, watch and learn. As shown in this drawing, all right, the concave or converging mirror, as shown here, is always facing to the left. In other words, the object is positioned to the left of the reflecting side of the mirror. Notice that the reflecting side of the mirror is curved inward. All right. So that is how we model a concave or converging mirror. It is called converging because uh, when the reflected rays, all right, are traced, okay, they tend to converge somewhere in the principal axis. So the imaginary line that connects the vertex of the mirror, the focal length, or the focus, as well as the center of the radius of curvature, all right, they are all connected by this so-called principal axis. On the other hand, in a convex, also known as diverging mirror, notice that the reflecting side of the mirror is curved outward. All right. So the object is located to the left of the reflecting side of the mirror. It is called diverging because uh, the reflected rays, all right, when traced, they tend to diverge or move away from the principal axis. In solving problems on spherical mirror, we have to follow some sign conventions. All right. So for the focal length, small letter f, uh, it is positive when the mirror is concave and it is negative when the mirror is convex. And that's also true for the radius, small letter r. All right. It is also positive when the mirror is concave and negative when it is convex. For the object distance, denoted by DO, okay, usually the object is located to the left of the mirror. All right. So that means the object is always considered a real object. But there are some cases, especially when we are analyzing combinations of uh, lenses and mirrors, where the object may be considered a virtual object. Hence, the sign of DO can also be negative. Now, for the image distance, DI, in the case of concave mirror, uh, the DI can either be positive or negative. All right. So when the image is located in front of the mirror, it is considered a real image. Hence, DI is positive. But when the image is formed at the back or behind the mirror, where DI is negative, we say that the image is virtual. In the case of convex mirror, the image is always virtual. Hence, uh, the DI will always come out to be negative. Now, for the lateral magnification, small letter m, in the case of concave mirror, the orientation of the image can either be positive or negative. So when small letter m is a positive or has a positive orientation, it means that the image is erect or upright. When it is negative, that means the image is inverted upside down. In the case of convex mirror, the lateral magnification, small letter m, is always positive. That means that the image is always upright or erect. Now, for the absolute value of the lateral magnification, in the case of concave mirror, all right, small letter m can either be greater than 1, all right, which means that the image is bigger than the object, or we usually say that the image is enlarged. When m is exactly equal to 1, it means that the image has the same size as the object. And when small letter m is less than 1, we say that the image is smaller than the object, or it is reduced. Now, for convex mirror, the absolute value of the lateral magnification is always less than 1, where we say that the image is smaller than the object, or it is a reduced image. Another important hint when we are analyzing or solving problems on spherical mirrors. All right. So in this table, we have summarized the different cases when the mirror is concave. All right. And uh, when the mirror is convex, there's only one case. That is, all right, if the object is at a finite distance in front of the convex mirror, all right, then the image is always formed behind or at the back of the convex mirror, and it's always virtual. In short, its image distance will always come out to be negative, all right, and its lateral magnification will always be positive, which means that the image is always upright or erect, and that the absolute value of the magnification is always less than 1. So meaning that the image formed by a convex mirror is always reduced in size. So that's only one case for the convex mirror. But for concave mirror, there are 6 cases, all right? Depending on where the object is located. So, for instance, in case 1, all right, this is where the object is located between the vertex and the focus, right? An example of this situation is when we are using a concave shaving mirror, all right? So, the mirror is placed very much close to your face while you are shaving. So, the image of your face will always be formed behind the mirror. In other words, its DI will always be negative. All right. In short, it is always a virtual image, and that this image is always upright or erect, and it is always enlarged. Right. Now, cases 3, 4, and 5. Okay. Uh, these are the 3 cases where the image is always a real image. All right. Real image and always inverted. In other words, uh, the orientation of the image is such that it is laterally uh, or it is inverted upside down. All right. When the object is um, erect, then it follows that the image will always be inverted. All right. But the size of this image, all right, can either be enlarged, same size, or reduced. All right. So it's important for us to remember, okay, the only case or cases where the image is real and always inverted are the three cases, case 3, case 4, and case 5. All right? So when the object is located between the focus and the center, all right, then we expect that the image will always be real and inverted, and it is enlarged. When the object is exactly equal to twice the focal length, then that means the image is also real, inverted, and has the same size as the object. But when the object is located at a finite distance beyond the radius or twice the focal length, then again, the image is real and inverted, but it is reduced in size. Right? And case 1 is the only case where the image is virtual. Right? Virtual but erect and enlarged. So, the other two cases, case 2 and case 6, are those cases where there is no distinct image form. All right? That is, the object is located at the focus so that uh, the incident rays from the object, okay, when reflected, will not intersect. They will all be parallel to each other, so there will be no distinct image. And in the case of the object located at an infinite distance, such as, for example, the sun, all right? The sun's location may be considered infinite, okay, with respect to the earth. So the image of the sun, when seen through a concave mirror, all right, there will be no distinct image. In other words, the sun will just form a very bright spot, all right, at exactly equal to the focal length of the mirror. So there is also no distinct image. All right? So uh, it is important that you memorize these 6 cases, all right, for the concave mirror. For the convex mirror, since there's only one case, it's not that hard to memorize this case. Question number 1. A concave mirror is to form an image of the filament of a headlight lamp on a screen 8.00 meters from the mirror. The filament is 6.00 millimeters tall, and the image is to be 24.0 centimeters tall. Question letter A. How far in front of the vertex of the mirror should the filament be placed? Question letter B. What should be the radius of curvature of the mirror? Question number 2. A mirror on the passenger side of your car is convex and has a radius of curvature with magnitude 18.0 centimeters. Another car is behind your car 9.00 meters from the mirror, and this car is viewed in the mirror by your passenger. If this car is 1.5 meters tall, what is the height of the image? And question number 3. You are in your car driving on a road at 25 meters per second when you glance in the passenger side mirror, which is a convex mirror with radius of curvature 150 centimeters. And you notice a truck approaching. If the image of the truck is approaching the vertex of the mirror at a speed of 1.9 meters per second when the truck is 2.0 meters from the mirror, what is the speed of the truck relative to the road? The concave mirror is to form the image of the filament of the car's headlight lamp on a screen 8.00 meters from the mirror. So that means the image distance di is equal to 8.00 meters. We are also given the height of the filament, 6.00 millimeters, and the height of the image, hi equals 24.0 centimeters. And the target variables are, for letter A, the object distance, DO, which is how far in front of the vertex of the mirror should the filament be placed. And letter B, the radius of curvature denoted by small letter r. And for our solution, we use the formula DO equals DI times HO over HI. Alright? Now, this is actually based on the formula for lateral magnification small letter m, which is equal to negative DI over DO or HI over HO. Alright? So, in determining the object distance DO, we disregard the sign here already. So, that means we are just interested on the magnitude of the object distance. Right? So, substituting our given quantities, DO is equal to 800 point centimeters. Alright? There's a dot here to emphasize that this quantity has three significant figures, and that's to be multiplied by 0.600 centimeters. Alright? We just converted 6.00 millimeters to centimeters, and that's divided by HI equal to 24.0 centimeters. So doing our math, we will get the value or magnitude of the object distance equal to 20.0 centimeters. And for letter B, okay, to compute the radius small letter r, we use the formula, all right, 2 over r, okay, because the radius r is in fact equal to twice the focal length, all right, and the reciprocal of the focal length can also be expressed as 2 over r, and that is equal to the reciprocal of the object distance plus the reciprocal of the image distance. And plugging in the quantities, we have 2 over r equals 1 over 20.0 centimeters. Right? This is our computed object distance plus 1 over 800 centimeters. The DI 8.00 meter, when converted to centimeter, that's 800 centimeters, also in three significant figures. So doing our math, we finally get the value of the radius small letter r equal to 39.0 centimeters in three significant figures. For question number 2, the side mirror of the car is a convex mirror, and it has a radius of curvature r equals negative 18.0 centimeters. The object is another car 9.00 meters from the mirror. All right. So the object distance DO equals 9.00 meters. This other car from behind is 1.5 meters tall, which means the height of the object, HO, is equal to 1.5 meter, and we are asked to find the height of the image, right? Or the height of the image of the car from behind when viewed in the mirror. That is denoted here as HI. But before we can find the height of the image, we first have to find the image distance, DI, all right? Using this derived formula for the mirror equation, all right? So the derived formula is that the image distance di is just equal to the product of the focal length and the object distance divided by the object distance do minus the focal length, small letter f. So substituting our data into this formula, we have the focal length is half of the radius, all right? That means the focal length is negative 9.00 centimeters multiplied by the object distance, which is 9.00 meters or 900 point centimeters, all right? So this will be divided by the object distance, 900 point centimeters, minus negative 9.00 centimeters. All right. So there's a double negative. So that becomes plus. All right. So simplifying, we'll get the value of the image distance di equal to negative 8.90 centimeters. Right? So now we can proceed in computing for the image distance hi, again using the formula based from the formula for lateral magnification. Hi equals di multiplied by the ratio HO over DO, right? So substituting, we get di, which is negative 8.90 centimeters, all right, multiplied by HO, which is in centimeters, is equal to 150, all right, centimeters. And that's divided by DO, DO being equal to 900 point centimeters, right? So again, doing your math, we will get the magnitude of the height of the image HI equal to 1.5 centimeters into significant figures. For question number 3, we are talking about a convex side mirror whose radius, small letter r, is equal to negative 150 centimeters, on which you notice a truck approaching the vertex of the mirror at a speed of 1.9 meters per second. Your car's speed of 25 meters per second is in fact also the speed of the mirror relative to the road. So we label that here as V of MR. The truck is actually 2.0 meters away from the mirror, all right? When you see it approaching at 1.9 meters per second in the mirror. So that means the object distance, all right, DO is the distance of the track, all right, equal to 2.0 meters. And our target variable is B sub O, in other words, the speed of the object, which is the truck, which we also label here as B sub TR, or the speed of the truck relative to the road. Right? And the first thing that we have to find is the image distance DI using this derived formula for the mirror equation. That is, DI equals the product of the focal length and the object distance divided by the object distance minus the focal length. And substituting the given quantities, we get negative 75 centimeters, which is the focal length of the convex mirror, multiplied by the object distance in centimeters, which is 2.0 times 10 to the second power centimeters. And then divide this by that object distance, 2.0 times 10 to the second power centimeters, minus the focal length, which is negative 75 centimeters. So we have a double negative sign. That means this becomes plus. So simplifying, we'll get the value of the image distance DI equal to negative 55 centimeters, or in meters, it is equal to negative 0.55 meters. Using the mirror equation, 1 over DO plus 1 over DI equals 1 over F, we can determine the instantaneous speed labeled as the derivative of dO over dt of the approaching truck relative to the mirror by taking the derivative of both sides of the mirror equation with respect to the time t. So, we take the derivative of 1 over dO as negative of the derivative of dO over dt over dO squared, okay, minus the derivative of di over dt over di squared, which is equal to 0. All right, because f is a constant, so the derivative of a constant is equal to 0. Transposing, the derivative of d over dt is equal to the negative dO squared times the derivative of di over dt all over the square of di. So substituting, in our data, we have the square of the negative 2.0 meters, all right, multiplied by 9.9 meters per second, all right, and their products will be divided by the square of di, which is 0.55 meters. So if you do your math, we will get the value of the derivative of dO over dt equal to 26 meters per second. So we say that this 26 meters per second is actually the speed of the truck relative to the convex mirror. Alright, so now that we know the speed of the truck relative to the mirror, okay, which is 26 meters per second, we can now proceed in getting the speed of the truck relative to the road, labeled here as v sub tr. And that is just equal to the sum of the speed of the truck relative to the mirror and the speed of the mirror relative to the road. That is, v sub tr is equal to 26 meters per second plus 25 meters per second, or v sub tr equals 51 meters per second. So this is our final answer to question number 3. And that concludes our tutorial for this topic. Till the next episode, mabuhay. Masya Allah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.